All right, last time we were in the middle of working on graphs of functions, and we had stopped at the point where we were looking into behavior of functions. And the specific behavior that we were referencing was whether functions had increasing or decreasing behavior, I believe. Does that sound right? We were looking here at this, and we had done this example. Okay? So I was going to show you another sort of way that this can be presented without using, or maybe aside from using, intervals. There is one other option. And it looks something like this. This particular problem actually labels the points with variable letters, like A through E. So we're going to consider the function below, and we're going to identify the behavior. This is actually really friendly because you don't have to identify where it starts and where it stops. You're just looking at where it starts and it stops as it's given and deciding, is it increasing, decreasing, or constant? So after you get that jotted down, I know it takes a minute to write all of that in, go ahead and write down on parts A through D, increasing, decreasing, or constant, and then check with a neighbor to make sure that you remember where we left off last time. After you make your decisions, increasing, decreasing, or constant, see if someone nearby you can confirm that you have the same thing they do. Okay, what do you guys have on the first one? Is it increasing, decreasing, or constant between A and B? Decreasing. How about from B to C? It is increasing. Remember, reading from left to right. And then from C to D? Decreasing. And then D to E. Constant. Good job. So when we're taking a look at behavior, another aspect of behavior is what happens at these locations where it sort of changes direction, right? Like B and C are interesting locations where it changes what it's doing. It was increasing, now it's decreasing. Or even right here has some measure of interest to us because it's changing from decreasing to constant. These are the points where I'd like to focus our attention in our next bit of material. These are what are called extrema. They're extreme points. And what it means that is in a nearby area, they're either the biggest, or in a nearby area, they are the smallest value. So these are actually called local maximums and local minimum values. Because locally, nearby, they're the biggest or the smallest thing there is. So more mathematically sound would be that a local minimum is a y value that is the smallest in a nearby area. You can think of it as a valley. And a local maximum is a y value that is the largest in a nearby area, and you can think of it as a peak. Peaks and valleys. Some books will not use the word local. They'll use the word relative. Relative maximum, relative minimum. So to give you some idea concretely, like real life kind of stuff, we use this all the time. My mom is about 5'1" at this point. My mom truly believes that I am tall. Some of you gentlemen have stood up next to me up here at the front of the room, and your opinion is a little different than that, right? I'm 5'4"-ish. You know, I'm in the shrinking stage of my life, right? You guys know that? After you get to a certain age, you start to sort of shrink back down a little bit. Yeah, I'm there. So I'm 5'4"-ish. My mom would tell you that I'm tall. And the reality is that in my family, I am the tallest female. Literally, for reals. My sister's about 5'2". I have a sister-in-law who's probably not even quite 5 foot. Yeah. So in my family, I'm relatively tall. But she had this sort of moment when she came to visit us when we lived in Ohio we lived there for about 3 years, and we were youth pastors at a church. And just about all the youth, male and female, all of them were taller than me. And these are kids, right? They're high school kids or junior high kids. And I had to tell my mom, see, I'm not tall. It's all relative, right? It depends on the comparison that you're making. Who are you comparing these aspects to? So that's what relative extrema or local extrema are, is in a nearby area. So if you take a look at this graph, you will see that it has some of those locations, those places where it goes from increasing to decreasing, where it has peaks and where it has valleys. And those locations are our interest points right now. So our first interest point would perhaps be this one if I'm sort of moving from left to right. What kind of a point would that be? It's a minimum, right? This is a local minimum. And what is the location of this local minimum? Right, it's at -4, -5. We're just going to identify them, and then we'll go back and answer the actual questions. The next point of interest would be a peak. It's this one. So that one would be considered local what? Maximum. And what is its ordered pair location? -1, 1. Good job. And the last point of interest in this regard anyway would be this one. And it is a local minimum. Good. And its ordered pair would be what? 2, -5. So these are our three local extrema, or three local extreme points, three local extreme values. But we need to answer the questions that are asked. This question says, find all values at which f has a local minimum. The at which means where is it happening? You can either write the ordered pair, which would be fine, or you could really just write the x value, because that's the location, because these are functions, right? The x value tells you where you are. So you could either write, for local minimum, that this is happening at x equals -4 and x equals 2. Or, if you'd rather, you can write that it's happening at -4, -5 and at 2, -5. Either of those would be acceptable answers for the question. And then the values at which f has a local maximum would be at x equal what? Yeah, x equal -1. Or if you'd rather, you can write that it is at -1, 1. Now we can have that discussion and we can say, relatively speaking, am I tall? And it depends on the comparison that we're making, right? I mean, like in my house, I'm also the tallest female, but barely. I have a 18-year-old daughter who's not going to pass me, but she thinks she has because she has really tall hair. It's like you don't get to count your hair. It doesn't work like that. But I have a 13-year-old daughter who will pass me because she's already super close. All right, so right now I'm still tall in my house. But there's also those cases where we can say, all of us, and you can go, that person's tall, and people aren't going to argue with you about it, right? Right? Michael Jordan, and I don't mean the Michael Jordan here on campus. I mean the Michael Jordan basketball player. Just for clarification. Michael Jordan, if you said he's tall, nobody's going to argue with you about that, right? Okay, so those people, in my sort of scenario, would be what we would consider almost like absolute cases. We're not having a discussion about whether he's tall, right? He's tall. So in our scenario with our values, those are what are called absolute extrema. Absolute extrema, or absolute maximums and minimums, are the smallest or largest y value for the whole graph, the whole function. It is as high as you go. It is as low as you go. There's no question. So two types of extrema, relative and absolute, or local and absolute. So just going back real quick to the previous slide, if I were looking at this particular graph, there is a relative minimum. There's two of them, right? And those 2 points are also absolute minimums. They're as low as you go. There's no further point down on the graph of this function. There's not. So those are also absolute minimums. But this point, while it's a relative maximum, it is not an absolute maximum because this graph continues on upward on the edges. There are bigger y values. So we would say that this graph doesn't even have an absolute maximum. And that's totally possible. So let's do an example where we're actually looking for those features. Similar graph as the last one. We're looking for the absolute maximum and the absolute minimum. So let's start with absolute maximum. What can you tell me about this graph's biggest value? Okay, right here is what Sarah's proposing. Oh man, but there's this sort of arrow thing going on that keeps that from being the case. Now, if that arrow actually had ended in, say, like a point right here, then you'd be good to go, right? And some of your examples will do that, and you will actually have the answer would in fact be the -4, +5 coordinate, okay? This one's not. So we don't have one, right? There is none. It doesn't exist. Some kind of language like that is what you would say here. But there is an absolute minimum. Where is that absolute minimum happening? Yeah, down here at 4, -2. I want to show you one other thing, which is why I chose this example. Let's pretend for a moment that the graph stopped here. None of this was here. Just, it's not there, okay? Just pretend for a minute. I'd have an absolute maximum, the one that we had said before, right? It would be there. This point right here would be the lowest point. But there's a problem. What's the problem? It's an open circle, which means it doesn't ever actually get there, right? You can get as close as you can possibly want, but you never actually arrive at the value negative 3, 1. It doesn't get there. It's an open circle. So if you were looking for the absolute minimum on this one, because it's an open circle, it doesn't exist either. Crazy, right? So those open circles act kind of like those arrows do in terms of the types of answers we get. Okay, one more example before this section's finished. And I think you guys are going to like our next section. I really do. I think you're going to enjoy it. So let's try this question. We have a graph, and we're going to identify some different aspects of the graph, okay? So in this graph, if we were looking for maximums and minimums, we could do that. If we were looking for increasing and decreasing, we could do that. If we were looking for relative or local versus absolute, we'd have all those things we could look for in this graph. But we're asked a little bit different questions. We're asked about where values are positive and negative. Now, please remember that this notation means y values. So when it's asking you about this right here, it's telling you what about x? What is x equal to? 5. So over here on your graph, can you find where you are? Can somebody describe it for me if you're at x equal 5? You're on the far right, aren't you? This point right here. This is the point when x is equal to 5. So the question here is asking, is the y value, when x is 5, is the y value positive or is it negative? And it's positive. In fact, I know I could also ask you what the value is, and you'd be able to tell me what is the value. It's 1. When x is 5, y is 1, and that number is positive. Now, looking at the graph, part B asks, where is f of x equal to 0? F of x again means what? The y value's 0, and you're trying to find the x that goes with that. So do you see any locations where the y value is 0? Yeah, it's this point where it crosses the x-axis, right? At this point, my y value is 0. And the question asks, for what x values does that happen? So what is the x value where that happens? One, right? The x is 1 when the y is 0. C. For what values is f of x less than or equal to 0? What does less than or equal to 0 mean? That it's negative. So everybody good with that? Negative values. So on my graph, everything that is below the x-axis would be negative values, right? So all of this is negative y values. Everybody good with that? Where do the negative y values start? I think they start right here, don't they? Think left to right. Remember, we're always going to read our graphs from left to right. So the furthest left point that we go is where it would be starting. So it starts where I've circled at, what is that, negative 2, negative 1. And it ends right here at 1, 0. So everybody good with that? But it asks for the x values, right? So at what x value does it start? Negative, what was it? 2. All right, good. Negative 2 from here. And at what x value does it end? 1. 1. The y value is 0. Right here is the curve I'm on. I feel like I've written too much on my graph. Now we can't see it. I start right here, and I end right here. The x value here is -2. The x value here is 1. Is that okay, Megan? Okay. Everybody else? Oh, yeah, I was like, there's a lot going on in my graph at this point. Everybody else good with that? Okay, so it starts at -2, and it ends at 1. And because this says less than or equal to, it's okay for it to actually equal 1. Because when x is 1, y is equal to 0. And at the other location, I'm still completely beneath the graph, and I have a closed dot, or a filled in dot, so it's also a bracket. Okay, interval notation. But the next piece wants to know where it's greater than 0. So for that one, where will it start and where will it end? Where does it start, moving from left to right? Where does it start being greater than 0? Yeah, it would still be at the 1. And where does it end? Yeah, now some of our graphs don't end. They have arrows and they keep going. So that's when we put the infinities, right? But this one stops. It stops where I've circled the stopping spot, right? The 5, 1. So this one starts at 1, 0. And it ends at 5, 1. But again, it wants to know the x values, not the ordered pairs, right? So at what x value does it start? 1. And at what x value does it end? 5. Now at 1, we're actually on the x-axis, right? So at 1, the y value is 0, but this says that I need to be greater than 0, yeah? So will I get to use a parenthesis or a bracket next to the 1? It's a parenthesis, because it can't equal 0. It just has a greater than sign. But on the point 5, I'm still above the x-axis, right? And I have a closed dot. So I can equal that particular point 5. I'm not back on the x-axis. I'm still above. All right, are you guys ready to shift gears a little bit? Let's do it.